chemistry. Here we are in this virtual situation. It's not crazy. I'm not crazy about it, but you know, hey, it is what it is. We're just gonna make do. We got 5 weeks left to go. Probably 4 by the time you're watching this. We're just gonna dig in and try to figure out how to make this work. Hopefully you're gonna enjoy seeing me rather than all those other teachers. It's gonna be much more exciting. What we're gonna do today, this is gonna be a quick video. I just wanna go over the pictures and graphs worksheet that you have been working on and turned in. I want you to have the right answers on this, and I just want to point out some of the things that I think are the most important on this. You saw the 20-minute video where they kind of went through and highlighted the different graphs. But when we look at this, first off, this is going to be a mass spectrogram, mass spectrum. And we talk about this and joke about it. What do you think a mass spectrometer measures? Well, obviously it's mass. And so the higher the peak, the greater the abundance. And so you probably can't read this too much just looking on the video, but you have this sheet in front of you. So we have neon right here, 20, that has obviously the greatest percentage. I think it says, I can't even read it, it says 90.92, I believe, percent. Then you have another peak, barely itty bitty little peak right there, and then a third peak right there. Each peak represents an isotope, a different isotope. And so if we want to calculate the average atomic mass, remember it's an average based upon the abundance. So when we go through and calculate that, we just go through and we calculate the percent, and remember to move the decimal, times the atomic mass. Now this will either be given on the screen like it is here, it's that top number. The mass number and the atomic mass, the 3 sig figs, are going to be the same thing. Okay? The atomic mass and the mass number to 3 sig figs will be the same thing. So we just go and we put those 3 in, you get these 3 values, and you can see that the average. Now notice again, since it's an average based upon abundance, since the majority of it's neon 20, the average comes out closest to 20. You have just a smidgen more of the heavier ones, so as a result, it's just a little bit more than 20, but not much. It's an average based upon abundance. Okay? So, now, here we have the emission lines then, so if I move this out of the way, here now we have, well, I gave the answers away. If you remember from your electromagnetic radiation, okay, you have infrared, visible light, ultraviolet, X-rays, cosmic rays. So ultraviolet are higher energy than infrared, higher energy and visible. These are the ones from the sun that hurt you and cause sunburn and skin cancers. So we know UV is the high energy. Well, the bigger the transition, the higher the energy. So when electrons go all the way down to this first energy level, remember the energy levels are not evenly spaced. So there's a big jump between the first and the second. Not as big between the second and third, and then they get smaller and smaller. And that has to do with math. Remember, we're dividing by n squared in calculating these energies. And so as a result, infrared is going to be the lowest energy, which means the longest wavelength. So you do need to know the relationship between energy, wavelength, and frequency. We have the 2 equations. E equals h nu, and C is equal to lambda nu. So this is a direct proportion. This is an inverse proportion. So that means that as the energy goes up, as you have a bigger change in energy, that means you're going to have a higher frequency. But if you have a higher frequency, you're going to have a shorter wavelength. So this question is asking for here, the emission, you don't have to memorize, you just kind of need to know the relationships here. Okay, so when we go and look then at the questions, okay, as far as which is going to have the greater wavelength, let me cover this up right here. So, bigger energy equals higher frequency. Higher frequency is going to be, so what's the question asking the answer? The emission line is much serious as AP, do you need to know? This just says label those, okay? So we label them based upon the energy. So would the wavelength of light be longer or shorter for lithium? N equals 2. Well, lithium's got 3 protons, hydrogen only has 1. And again, if you recall in the equation, E, you do not have to know this equation. 2.18 times 10 to the minus 18th divided by n squared. But we have this Z up there. Z is the atomic number. We only use that, we only did this for hydrogen where Z is 1, so we didn't even hardly put it in there. But if I multiply this by 3, you can see that this is going to be a bigger number. So the energy transition between lithium 2 to 1 is going to be a greater transition, a greater energy change than when n equals 1. As a result, lithium is going to have a higher energy, therefore it's going to be a shorter wavelength. All right? Conceptually, that's all you have to know. More protons, bigger energy change. You'll never have to do the math with this equation. However, you may have to do math with these 2 equations. Okay? Remember, C is the speed of light. H is Planck's constant. Both of those are given on the equation sheet. This is your frequency. This is your wavelength. Okay? So you should be able to do equations with those 2 things. You need to know the relationships here. You do not have to know that one. All right. Now, IMFs. Okay? One side of the curve represents the attractive forces. Okay? So, let's see here. One side of the curve represents increased attractive forces and the other increasing repulsive forces. Okay? So if I look here at this, well, let's move it down, move it up a little bit. Okay? So if I'm looking here, here's one atom, okay, just any 2 atoms. Here's one atom, here's another atom approaching it, okay? And so as it begins to approach, there starts to be an attraction of these electrons to this nucleus. The attraction is maximum right down here. This is the lowest potential energy. Remember, in nature, everything wants to be in that lowest possible energy state. As they start getting closer and closer and closer together, now the nuclei begin to repel because they're both positive, and we get to repulsive forces up above this line. But your bond length, the molecules, this is going to be the distance from here to here. That's going to be your average bond length. This graph shows up on the AP test a lot, so you need to be familiar with this. That it's going to be the lowest part is where the bond, that's where the bond is going to form right there, where you have the lowest potential energy. That's the most stable arrangement right there. It's going to be vibrating kind of back and forth in this, attractive, repulsive, attractive, repulsive. So this will be your average bond length. Okay, it's average because it is vibrating. And we never talked about this. I was going to go over this with the review, but to measure bond's length and bond strength, use infrared. Electronic transitions between energy levels. Okay, so what we're just doing up here on this with the different series, those are going to be UV light. Okay, and then microwaves, and the way I remember this, microwaves measure the rotation of molecules, how much they're spinning, how much they're moving, and the rotation of the molecules. And the way I remember that is because microwaves always have the little table on the inside rotating. So microwaves measure the rotation of molecules, IR measures bond length, and visible light and UV measure electronic transitions, the electrons moving from one energy level to another. I doubt seriously that that would be one of the 2 questions that they chose to ask, okay, because that's pretty random. So I pray that they're not going to do that, but that was something we were going to cover. All right, moving on. It says, okay, what's it going to look like then if it was a triple bond? Well, we know that triple bonds are stronger than double bonds. So here's my single bond. Well, if I have a triple bond, and also in terms of bond length, triple bonds are going to be closer together than a double bond. So I'm going to have to make a deeper well, and it's going to be a little bit farther to the left, so it's just going to come down. Oh, I didn't go far enough left. And it's going to look something like this, to where this would be the bond length then for the triple bond. And we'll see this on the next one, but the triple bond is just going to be the deeper the well, the stronger the bond. Okay? The distance from this to the bottom of the well is the bond length. Those are the 2 things you need to know this. This one again shows up a lot on the test. So when we look at the next one, oh, went too high. There we go. So now I have to justify between iodine, chlorine, and nitrogen. Now I've gone ahead here, they are labeled. But why do you think this is nitrogen? Okay? What type of bond do we have in nitrogen? Well, we know that it's going to be a nitrogen triple bonded to nitrogen. You're expected to know that nitrogen is triple bonded to itself. And then iodine and chlorine are both halogens, and so they're both single bonds. Iodine bonded to iodine, chlorine bonded to chlorine. Okay? So they're both single bonds, but iodine is a bigger atom than chlorine, and so the bond length is going to be greater and the bond strength is going to be weaker because they're just a little bit farther apart. Coulomb's law. Okay? Charges are the same, everything's the same, and they're just going to have greater distance. And so as a result, the iodine is going to have a longer bond length, and it's not valley, it isn't quite as deep because it's not going to be quite as strong. This is something that I would just make sure that you know. Again, you get 2 questions. Now, I have no idea what 2 questions they're going to ask, but that is something that they could throw in there. That is something they ask a lot. It's just good to know. All right. So, you miss being in the class, don't you? Oh, I know you do. Okay, so now this says, well, what's the bond energy of one molecule of nitrogen? Well, the bond energy is going to be right here, so we just read it, and since it's 200 for every one, it's 40, 80, 120, 160, 200, so this is going to be a 40, so it's going to be negative 940, or 940 kilojoules. That's the amount of energy you would take to break that nitrogen triple bond. You just read, that's what this is right here. This is your bond energy. All right, now, let's get this moved up. So again, here's your vapor pressure curves. Explain why the vapor pressure increases with increasing temperature. Remember, vapor pressure is the pressure exerted by the vapor above a liquid. The faster a liquid evaporates, the more vapor there is, so the greater the vapor pressure. Now, so if something has weak attractive forces, it evaporates quickly, it's got a lot of vapor, it's got a high vapor pressure. If it's got strong attractive forces, it evaporates slowly, and thus there's not as many vapor molecules above the liquid, and it's got a lower vapor pressure. So, if we look here at ethane, C2H6, compare that to water, well, we know that's a hydrocarbon. Well, the only type of attractive force in ethane, the hydrocarbon, are weak London forces. And so water, we know, is polar with hydrogen bonds, much stronger attractive forces, so the ethane is going to have a higher vapor pressure. At any given temperature, it's going to have a higher vapor pressure than the water is. Okay? So, it's all about attractive forces. That's an important graph, vapor pressure. That's another, that graph could very easily show up. So as temperature increases, the kinetic energy increases, so molecules evaporate more quickly, which means there's more vapor molecules, so there's more vapor pressure. All right, and then here's just your explanation why. Well, we already kind of talked about that. Ethane only has LDFs, water's got all 3. Much stronger attractive forces, therefore it's got a higher lower vapor pressure. Okay? Now, indicate which curve is likely water. We already did that, talked about that. Have those labeled. Okay? Now, sketch on the curve where you would expect for ethanol. Well, ethanol, where do they show ethanol? Ethanol's over here. And you see the OH right there. That's key. The OH tells me that, hey, I got hydrogen bonds, which tells me that it's going to have stronger attractive forces than this. But it's also got all this nonpolar part, so it's not going to be as polar. The hydrogen bonds aren't going to be as strong as in water. Very few are as strong as in water. So that means the attractive forces for ethanol are somewhere in between ethane and C2H6. So when we plug that in, our vapor pressure is going to be somewhere right in here for C2H5OH. Okay? So, pretty straightforward. The stronger the attractive force, the lower the vapor pressure. So vapor pressure and attractive force. Now remember boiling point. The boiling point occurs, okay, when it's 1 atmosphere. So that's the boiling point, that's the boiling point, that's the boiling point of each of those substances right there. The stronger the attractive forces, the lower the vapor pressure, the higher the boiling point. You must know that relationship. I would bet of the 2 questions, somewhere that's going to be asked in those questions, okay? The relationship between vapor pressure, boiling point, and attractive forces. All right, so there's the second page. Third page, same still, more attractive forces. Let's erase this out of here. Okay, now once again, this graph is very difficult to kind of see based from here. Okay, but you can see that there's a general trend line going up as you increase the atomic number. The vapor pressure, pardon me, these your boiling points are increasing. Okay. However, we have some anomalies up here of water, HF, and H3. Well, water, H2O, HF, and NH3. What type of bonds do all of those form? When in doubt, the answer is always, you're screaming it in your room right now, I know, the answer is always hydrogen bonds. So, because these 3 can form hydrogen bonds with each other, with themselves, okay? So water molecule, hydrogen bonded to water molecule, hydrogen bonded to water molecule, it's got a very high boiling point, higher than normal, okay? Most of the time as molar mass increases, because LDFs increase, the boiling point is going to increase. But these are small molecules, but because they can form hydrogen bonds, they have unusually high boiling points. So they're anomalies, they go against the general trend. Always look, when there's a difference in boiling points, always look for the general trend. The other thing to look for, when comparing boiling points versus attractive forces. Okay? Number 1, look at the data. They're always going to give you some data. Look at the data. The highest boiling point equals the strongest attractive forces. Let's say IMFs. Okay? Now, we normally say LDFs are the weakest, and then dipole-dipole, and then hydrogen bonds. However, there are sometimes they put in here, they give you an example of a big nonpolar molecule whose LDFs are strong compared to a small polar molecule that might even have hydrogen bonds. Okay? If the boiling point of the nonpolar is higher, that means that the LDFs of that one are stronger than the combined IMFs of the smaller one. Whichever one has the highest boiling point has the strongest IMFs. Hydrocarbons are always nonpolar, but the bigger they are, the stronger the LDFs, the more polarizable they become. So you always have to look at this. This is super important right here. And so we have anomalies here in boiling points due to hydrogen bonds, but if you're going to compare boiling points, always look at the data. Highest boiling point is always the strongest attractive force, even if it's nonpolar. It's just going to be a big nonpolar who's going to have stronger LDFs, will be stronger than the combined IMFs of the smaller molecule. Now, again, if the smaller molecule with hydrogen bonds has a higher boiling point, then you attribute it to the hydrogen bonds versus the LDFs. Whichever one has the highest boiling point, that's the one that's the strongest. So just go with that, okay? That's important. All right, so coming back to this then, explain it, all three form hydrogen bonds. CH4 doesn't form hydrogen bonds, therefore it just follows the normal trend right here. And so that just kind of explains that. Hydrogen bonds is the exception. All right. Now, you definitely need, what just happened? What just happened? There we go. I think my Elmo might have gotten coronavirus. It's acting up. Draw a picture showing the solvation, the hydration of MgCl2. Well, first off, the first thing you have to say is, what type of compound is MgCl2? Well, the first thing is a metal, so it's ionic. So when it goes into water, it's going to dissociate as ions. So remember, only draw one, well, in this case, one formula unit, which is going to be 1 magnesium and 2 chlorines. The magnesium we know is 2+. I tend to just like to draw a circle around it. And because it's positive, the water's going to come and attach. Which part of the water is going to attach? Yep, the oxygen. I hear y'all just answering out loud right in front of your computers, right in front of your phones. Your parents are thinking you're crazy. Mg2+. Now, Cl-, okay? Cl- would actually be a little bit bigger, but I don't want to draw that any bigger. But we'd have 2 of them. And again, since it's minus, the positive, so we would just put the waters around it. And 4 is plenty. Okay, you don't have to completely surround it, just put something. The biggest thing is you want to put the hydrogens and the oxygens. Don't label the hydrogens and the oxygens. We know water's H2O. Don't put charges on it. Just orient them in the right way. Draw it just like this. You have to do the same thing on this one. Okay, we've done that a bunch of times. You should be really familiar being able to do that. Okay? I'm trying to also get through this. I want this video to be as short as possible. So there's those diagrams. All right. Another thing you need to be able to do is identify, draw the lone pair. Well, I drew the lone pair in already. Each oxygen has the lone pair. Show the dipole attractions between water and the glycerol molecule. Make sure to show examples of the hydrogen and oxygen ends of the water. So again, we're right here. These are my OH groups. These are the polar. This is where the hydrogen bonds. So you're going to have a water molecule coming in here. And then this is going to be your hydrogen bond. You need to kind of just draw it just like that. Then you can have this one. Give it a little bit more space. It'll be there, and then the water, again, coming in there. Now, you could try to put hydrogens coming here, but this would be totally sufficient. More than likely, you would just have to be able to recognize where the hydrogen bonds are. Again, I doubt on the 2 questions you're going to have to draw anything out like this. You may just have to be able to identify, circle where the hydrogen bonds are, something along those lines. Okay? But glycerol, just for the record, glycerol is very viscous, very thick, because it has 3 places for it to hydrogen bond with itself. And so as a result, it's strongly bonded to itself, so it's a real thick. We did that at the very beginning of the year when we did density lab. All right, moving on. So now, same thing down here. Let me make this a little bit bigger. So now we have this, but now we have 2 places. Notice we have a nitrogen there and an OH here. So we have an NH and an OH. So water has a plethora of possible places to be able to form hydrogen bonds with this molecule. Does it tell me what the name of this thing is? It's a complicated molecule. It's got an acetic acid group on here, acetyl group, and it's got an ammonia and amine group here. So it's acidic on that end, basic on this end, but we didn't get to cover acids and bases, so you really don't know what that means. But anyway, so we know the water's going to come in here, bond. We're going to have a water come in here, form a hydrogen bond. A water can come in here and form a hydrogen bond. Okay? So, really and technically, I really don't like to do this, but I've seen it on AP tests that they give credit for this, that you could have that type of hydrogen bond there too, with a hydrogen attaching. Okay? But for sure, these three sites, again, be able to show the hydrogen bonds. All right. Now another important graph. I gotta zoom back in, make it all fit. Now I'm going to clarify, but I'm not quite sure what, there's some part of thermo that's not going to be on there, and I think there's some part of thermo that is going to be on there. I think maybe delta H will be on there, but not the delta S and delta G stuff, but I'm going to double check on that and I'll let you know, okay? But what you really just need to know is that when there's a slope on the line, that means the temperature is increasing. Temperature is a measure of average kinetic energy. That means the kinetic energy is changing here. So when we change kinetic energy, we use MCAT. When it goes flat, that means we're having a phase change. We're having a change in potential energy. We're breaking bonds, forming bonds. Change in potential energy, that's boiling and melting. So you just need to be able to recognize what's going on, okay? And so when we look at this, okay, melting and freezing are segments 2 and 4. Boiling and is 2, boiling and condensing is 4. 1, 3, and 5 is where we're having changes in kinetic energy. Here, this is where we would use Q equals MC delta T, and here we're going to use Q is equal to mass times your heat of fusion, or mass times heat of vaporization. Okay? This is kinetic energy, this is potential energy. Breaking bonds always requires energy. All right, when I had that all written down right there. Kinetic energy is MC delta T. All right, then here is my favorite graph. Label the curves and justify. So again, when we look here, okay, this is dealing with the speed, the molecular speeds of CO2 and N2. We all know if you have a big mass, you ain't going fast. If you have a big mass, you ain't going fast. So CO2 is 44 versus nitrogen 28. So obviously the nitrogen is going to be going faster. Now again, the height doesn't mean faster. The height means how many molecules have this much speed. It's how far to the right is the peak. So the slow one is the CO2, the faster one is the N2. Okay? Now, we can use that exact same graph though for the same gas at different temperatures. This would be T1 and this would be T2, where T2 is greater than T1. So you can either measure the speed of two different gases, whereas the smaller, lighter one's going to be moving faster, this peak's going to be farther to the right, or it can measure the same gas, let's just say it's CO2. This is temperature 1 of the CO2, this is temperature 2 of the CO2, okay? And as a result, it moves to the right. Now, it finally asks what's going to happen, okay? Well, it doesn't ask it on that one. Now, you didn't have to do number 6, okay? So now we come here. Oh, I have all my answers shown. Ooh, there we go. So now we have nitrogen, helium, and argon. 28, 4, and 40 grams per mole. Okay? So which gas has the greatest velocity? Well, again, you have a big mass, you ain't going fast. So the smallest, lightest is going to be going the fastest. So helium has the greatest velocity. Okay? It's the smallest one. That's your justification. Assuming the mass of those empty cylinders are all the same, so we have all the same cylinders here, okay? Which is going to be the greatest? Well, if argon's the heaviest gas, and remember, Avogadro's principle says equal volumes, these are all the exact same size, equal volumes of gases under the same conditions of temperature and pressure all contain the same number of molecules. So it doesn't matter how big each of the gases are in molecules, same number of molecules in each one. I have no idea. Let's just say there are 2 moles. There'd be 2 moles in here, and there'd be 2 moles in here. Okay? However many moles are in this one, they're all 3 going to be the same. Same container. Therefore, if they have the same net amount, obviously the heavier one's going to have weigh the most. Now, here's the trick question. Okay? Which has the greatest kinetic energy? Well, temperature measures the average kinetic energy. Since they all are at the same temperature, they'll all have the same kinetic energy. Not the same speed. Helium's going fastest, argon's going the slowest, but they all have the same kinetic energy. Okay? So you always have to differentiate. Same temperature, lighter's going faster, but they all have the same kinetic energy. That's what temperature measures. All right. Now we're going to go through this real fast because the odds of this being on there are really slim. Okay? What forces of attraction are broken during the dissolving process? Well, again, we have solute. Well, I already have it written out. Let's go fast. You know this one. We have the 3. Solute, solute, solvent, solvent, that's where they have to move apart. Breaking up is always hard to do. Breaking bonds always requires energy. These 2 steps are endothermic. The third one is exothermic. Your overall heat of solution is equal to delta H1 plus delta H2 plus delta H3. This would be delta H1. This would be delta H2. This would be delta H3. Remember, these 2 things are both positive. This one is always negative. So the sign of delta H is dependent upon which of these is greater. For an ionic compound, remember that the breaking, this is always going to be referred to as your lattice energy. And this is going to be your energy of hydration. Okay? Your energy of hydration. So as a result, whichever one is bigger. And so they could ask a question, draw a picture of the dissolving process. If the delta H is positive, that means the lattice energy was greater than the energy of hydration. If the delta H of solution is negative, that means the energy of hydration is those formation of hydrogen bonds. Or remember again, this attraction between Mg2 plus and the water, that's what we refer to as the ion dipole attraction. Ion to dipole attraction. And so that attraction right there, that's this. That is greater than the lattice energy, the attraction between the magnesium and the chlorine. If it's negative, if it's positive, then this one's greater. Most substances have a positive heat of solution. But again, go with what the data is telling you. All right, the rest of this is just interpreting this graph. And again, I'm going to go super fast because the odds of this being on there are very slim. Okay? And I don't really even like the premise of this. Most substances don't go supersaturated. You can't just add more than the maximum amount and make a supersaturated solution. They're rare, they're hard to form, and so the fact that it says, but it says a solution is made using 70 grams potassium dichromate. Well, here's potassium dichromate at 80 degrees. A saturated solution is going to have 60. They're saying the solution has 70, which means that it has more than the maximum amount, so it's supersaturated. On the other hand, at 80 degrees potassium nitrate, 80 degrees potassium nitrate, well, potassium nitrate 70 grams. 70 grams will dissolve at 40 degrees. So at 90 degrees, 80 degrees, you can have way more. I mean, that thing just, you might have unlimited amount up there at 80 degrees. So it definitely can hold more, it's unsaturated. Okay? Now, if you have three solutions, one is unsaturated, saturated, super saturated. And if I put one crystal into each one, okay, this question is kind of asking what's going to happen. Here, if it's unsaturated, that crystal is going to dissolve. If it's saturated, the crystal is just going to go to the bottom. If it's supersaturated, a whole bunch more is going to precipitate out. Remember, I did the sodium acetate, and if you want to look it up online, the supersaturated solution of sodium acetate, NaC2H3O2. It's kind of a cool, and that's what hand warmers, some types of hand warmers use a supersaturated solution because you have to put energy in to make it dissolve. So then when you mess with it and it recrystallizes, it gives off a lot of heat. Okay? So that's what happens in a supersaturated solution. The crystal begins to grow. And then, okay, the solution is supersaturated. And then here, if you cooled it down from 90 to 30, well then at 90 you can have 48 grams, at 30 you can only have 10 grams, that means 38 grams is going to precipitate out. And that's just from that graph also. This is why we put things in an ice bath. When we were trying to get a precipitate, we put it in an ice bath because we want to lower that solubility and cause as much of the excess to precipitate out. But again, we wouldn't get 100% yield because 10 grams was still soluble. Okay? So that's just a thought. All right. Moving on. We're getting there. Almost there. This graph, again, we've seen a bazillion times. You can know that with a catalyst, it's just going to lower the activation energy. So when we look over here on this graph, on this side here, if we increase the temperature, we're going to move the hump, broaden it out, move it to the right. So now there's a whole lot more molecules that have enough energy to overcome EA. If I add a catalyst, the catalyst lowers EA. So on this graph, EA is going to move then to the left. So now you'd have even all these molecules would have enough energy to overcome EA. So changing temperature moves the graph. Adding a catalyst moves the activation energy. We've talked about that a lot, but again, you know me, this Maxwell-Boltzmann temperature distribution graph, that's one of my favorites. All right. So now, I gotta leave the choices. So now I have an energy diagram, but it's got two peaks. So that tells me I have a two-step mechanism. The products are higher than the reactants, so I know it's endothermic. Since this is the higher activation energy than this, that makes this the slow step. Okay? So this is my slow step. Okay? This is reactants, this is products. We're going up in energy, so it's endothermic. Okay, so I find the one that says an endothermic two-step mechanism for the first step is slow. That's going to be B. Okay? Now, we go to this one. Here's my reactants. Here are my products. Therefore, the energy is going down, so I know it's exothermic. Again, it's two steps, but the second step is higher, so this is my slow step. So it's a two-step exothermic reaction where the second step is slow, so that's going to be E. Okay? Now, let's see if I can make this work. Yes. Although now you've seen the answers. So when I look at this one, well, here's my reactants, here are my products, energy's going up, so it's endo. It's only got one peak, so That means it's a one-step mechanism and one-step endothermic. Which one is that? Endothermic step, that's F. Okay? Well, I'm tired of dealing with all that. Let's just look here. So this one is an exothermic one-step. Okay? Exothermic, endothermic one-step. Here's a two-step exothermic because the products are less. And this is my slow step. And this is my slow step. Okay? So, again, I don't know how they're going to ask questions on this, but that's pretty easy, good to know. Super fast on this now. Know your y-axis. Okay? Zero order, it's concentration. First order, it's 1 over, it's the natural log of concentration. Second order, it's 1 over concentration. That's your y-axis. A catalyst is going to speed it up. Okay, let me see if I can get all three of them on here. Okay? This one is opposite, so the catalyst is going to be above. Don't worry about what the y-intercept, when they talk about what's the intercept, I've never seen a question dealing with that. But we always know that the slope of the line is equal to k. K is always positive. So this is a negative slope, so we're just going to take the negative, okay, the slope. So really k is the negative of the slope. Whereas on this third one, it's positive, and so slope equals k. All right. So we should know how to do that. Here's another one with kinetics, relating it back to the same thing with a catalyst. And then, shoot, we already did that. That was one we already did. Okay, now, I didn't really care for you to have to do this one. The only thing I would want you to know how to do is find the rate, instantaneous rate, by finding the tangent, slope of the tangent line at any point. Now, in order to determine what type of this is, you have to look at the half-life, okay? Zero order, here are your equations for the half-life, right here. So you might want to copy those down. This is the only one that's on the equation sheet, which tells me that this is the only one that you're going to really need to know. But here's the thing. Zero and second order, the half-lives change with concentration, change with time. First order, the half-life's the same throughout the whole reaction. That's how you tell that it's first order. The half-life stays the same. That's what I would take away from this. Now, I didn't like any of the graphs on part E for equilibrium, so we're going to skip over all that. Acids and bases aren't covered. And so then they just went to some just basic lab questions. Here's our Beer's Law. Beer's Law is a favorite lab. I am betting that one of the questions is going to be lab-based, okay? Because you won't be able to look it up anywhere, so you're going to have to be able to figure it out. It's going to be lab-based. Beer's Law lab is a good lab-based one, okay? I'll go through a couple of more lab-based problems and look at that, but here's my Beer's Law. Absorbance is epsilon BC, where it adds absorptivity constant, path length, and concentration. Don't worry about having to, you will never have to calculate this, okay? But the slope of my line, remember the slope, we keep these two things constant, that's my slope, y equals mx. So if we know the absorbance, we can know the concentration, okay? And what type of metals? Transition metals, because they have to have color. Remember, this will not work. Beer's Law doesn't work with colorless solutions, okay? And then here are just some examples of mistakes. If you had water in the cuvette, it's going to dilute the solution, lowering the absorbance. Okay? Don't worry about changing the wavelength, because that really just decreases your sensitivity, decreases the accuracy, but you won't have a question about that. Okay? If you have a fingerprint, that means less light's going to go through. It's going to increase the absorbance, which would make the point above the line, not below the line. Okay? And filling it above the line has no effect. It only reads just in that one spot. Okay? Then you get to exclude all of thermodynamics, H. Okay, so that's that whole worksheet. I want to go over one last thing, just to review other diagrams, and that's PEZ. You need to remember, and you have this worksheet, and I would go and try and dig out your notes and find this worksheet and just refresh yourself on it. But we have carbon and boron. Carbon has 6 protons. Boron only has 5 protons. Because carbon has 6 protons versus 5, its peak is a little bit to the left. It's going to be a little bit more strongly held. The height of the peak tells me how many electrons. Okay, so this is going to be my 1s for both of them. Okay, this is going to be my 2s. Okay, and this is going to be my 2p and 2p. Now notice again, let's see. Yeah, carbon has 2 electrons in the 2p. Boron only has 1 electron. So this represents, height represents 1 electron. This represents 2 electrons. But so what you need to know for PEZ, each peak represents a different sublevel. The height of the peak determines how many electrons are in that, and it's all relative. So you know S is always going to have 2, so this is the height for 2. Since this is half, it's only going to be 1. So the height tells me how many electrons. The position, if you were comparing two different atoms with the same sublevel, more protons, increased nuclear charge, means it's going to have a higher energy. Notice energy is 100 here versus 10. Energy is increasing this way. Notice that the ones closest to the nucleus are the hardest to remove. It requires the most amount of electrons. Okay, so just review PEZ. Okay, it's pretty straightforward. You just need to just make sure that you have those 3 things there. All right, that does it for this one. Hopefully that helped. Email me if you have any questions. I hope you're not going as crazy as I am being at home. I am ready to get out and see some people. It is very weird to sit here and talk to nobody. And by the way, if you're still watching, please subscribe to my channel. Thank you.